we're going to do notes for worksheet number 5 in the gas laws, and this worksheet is just for the honors chemistry kids. So if you're in modern chemistry and you see this and it starts to make your hair stand on your back, it probably is because we're not doing it in your class. So we're going to talk about Dalton's law of partial pressures. The total pressure exerted by a mixture of gases in a container is the sum of the individual pressures of each gas. The partial pressure is the pressure exerted by one type of gas if it were alone in a container. Partial pressure equation. The pressure total is the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas plus where the pressure of the first gas is really the moles of the first gas times R, which is the same for everything, times the temperature, which should be the same for everything, divided by volume. And where pressure 2 is the moles of the second gas times R times T divided by V. So the pressure total is the moles added up, total, the sum of all the moles, times R times T divided by V. And I just put in a little graphic here of total pressure. This container here has partial pressure of nitrogen, oxygen, and water in it. Water vapor, that would be. So let's do an example. This is problem number 1 from worksheet 5. A tank has a mixture of 3 moles of nitrogen, 2 moles of oxygen, 1 mole of carbon dioxide at 25 degrees Celsius and a total pressure of 10 atmospheres. Find the partial pressure in atmospheres of each gas. This problem is actually quite complicated, and we're going to do it in a series of steps. So, the first thing we need to find is the total volume. We need to find V total. And since we're given some total numbers, we're going to do that. We know PV equals nRT, so volume total must equal the moles total times R times T, all divided by the P total. The T is not total because I don't think there's such thing as a total temperature, but the temperature is the same for everything. So the moles total are 6 moles. And how did I get the 6 moles? I went 3 moles plus 2 moles plus 1 mole is 6 moles. R is always 0.0821 liters, atmospheres, moles, Kelvin, over the moles and over the kelvins. Those units are so helpful to make sure you are using the correct units in the other part. And temperature is 25 degrees Celsius, which is 298 K. You've got to be in K. And the pressure total, I believe it tells us, is 10 atmospheres. 10.0 atmospheres. So once we do all the math, let's make sure everything cancels K, ATM cancels ATM, mole cancels mole, and somewhere in there, there it is, we're left with liters. So we do all that math and we should get 14.7 liters. That is the total volume. So that was step 1. Now step 2, we're going to start finding the individual pressures. So again, we take PV equals nRT. The P in this case is going to be nRT divided by V. So let's do this one for nitrogen because I think that's the first gas listed. We'll do nitrogen. So you have 3 moles of nitrogen times the 0.0821 liters, atmospheres, moles, Kelvin, times the temperature, which is 298 K, all divided by the volume, which is 14.7 liters. And we'll do the math, and so we'll get the partial pressure for nitrogen gas, that's the proper way to write it, is 5 atmospheres. We are stuck with 2 sig figs in this one, so we had to round up. So I'm going to erase this and start over, and now we're going to do it for the next one, which is the partial pressure of oxygen gas. And in this case, it's going to be 2 moles of oxygen, that was given in the problem right there, times the 0.0821 liters, atmospheres, moles, kelvins, times the temperature, which we said was 298 K, all divided by the total volume of 14.7 liters. We do that math, and we should get 3.3 atmospheres of pressure. So that was for the pressure of oxygen, and we have one more left to go. This is the pressure of CO2. So So we find the moles of CO2, it's 1, so we have 1 mole times that 0.0821 liters, atmospheres, moles, kelvins, times 298 again. K, all divided by 14.7. So the only thing that's changed in each one of these was the number of moles. And the answer to this one is 1.7 atmospheres. Ta-da! There we are. A beautiful thing. Vapor pressure. Vapor pressure is the pressure of the vapor, which is gaseous, over liquid at equilibrium in a closed container. At sea level, water has a high vapor pressure than it would have at a higher altitude. What that means is at a higher altitude, the water could escape its container much more easily than it could at sea level, because at a higher altitude there's less pressure above the water because there's a smaller column of air. At higher altitudes, water has a lower vapor pressure. This is why water boils at a lower temperature at higher altitudes, because the water can escape whatever it's in much more easily than it could at sea level. Water displacement and gas collection. When gases are collected via water displacement, the gas in the collection bottle is not purely composed of that particular gas. In reality, the gas is a mixture of water vapor from the water and the gas being collected. So we must account for this by subtracting out the vapor pressure of the water. And the vapor pressure of the water is usually found in some chart that will be given to you. It could be in a book, it could be in a chart. And so you'll be given that pressure and you simply subtract it out. So let's do practice number 2 from worksheet 5. So given that the pressure of water vapor is 23.756 torr, here we are in torrs, at 25 degrees Celsius, write an equation for oxygen gas being collected over water. And this is a variable. This one's kind of a strange one, that's why I'm going to do it for you. So pressure total is actually equal to the pressure of the oxygen being collected, and unfortunately there'll be some water vapor in there because that water in there turns into vapor, so you have a little bit of both, of the water vapor and the oxygen gas. So if you just want the oxygen gas, you're going to have to isolate the oxygen gas, and it will be the total pressure minus the pressure of the water vapor. And I think in this case, you're not given the total pressure. This looks like an algebra class. So you leave the total pressure like that, and then you would subtract out this number that would either be given to you or you find it on a chart. And this one's in torrs. And that's the final answer. Strange, but true. So if you have another problem in your homework and you're given the water vapor pressure, you will have to subtract it out from the total to get the individual pressure. Moving on to KMT, kinetic molecular theory. So make sure you know the following. Gases consist of tiny particles, which are atoms or molecules. Number 2, the volume of the individual particles can be assumed to be 0 since they are so small. Number 3, the particles are in constant random motion, colliding with the walls of their container. The collisions exert pressure. The particles are assumed to not attract or repel one another. And number 5, the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. So the faster they move, the higher the temperature. Ideal versus real gases. So far we've considered all gases to be ideal. In reality, not all gases behave in an ideal manner. Lucky for us, the ideal gas law still gives us good predictions for most gases. That is the end of our notes for this chapter.